Hello everyone. Welcome to my YouTube channel on engineering mathematics.
In this video, I'm going to discuss overview of the concept of how to evaluate triple integrals over the given volume using spherical coordinate system. We will also see a couple of examples on it. So let us first understand when to use spherical coordinate system and how to use it. Note that we use spherical coordinates, that is r, theta and phi, only if the volume over which the integration is to be evaluated is of the spherical or oval shape. The relation between spherical and Cartesian coordinates is as follows. X is equal to r sine theta cos phi, y is equal to r sine theta into sine phi, and z is equal to r cos theta. Here r, theta and phi are spherical coordinates, x, y and z are Cartesian coordinates. So using these relations, one can write the order of evaluation dx, dy, dz as r square sine theta dr, d theta, d phi, where r square sine theta is the Jacobian used in the transformation from xyz system to r theta phi system. Now let us understand the limits for r, theta and phi. For that, we draw this sphere. Modulus r varies from origin to radius r or radius a. So r varies from 0 to a. Now we rotate this string for angle pi to get this semicircle. So here theta varies from 0 degree to pi. Then we rotate this semicircle. This we just obtained by rotating the string 0 to a. This semicircle we rotate for 2 pi angle like this from here to back here to get this entire sphere. So this is your phi, which varies from 0 to 2 pi. I hope you guys understood these angles. So we say r varies from 0 to radius a, theta varies from 0 to pi, and finally phi varies from 0 to 2 pi for entire sphere. These limits will change depending on the part of the sphere over which we are evaluating the integral. If we are evaluating only the half part of the sphere, then in that case modulus will vary from 0 to a, theta will vary from 0 to pi, and phi will also vary from 0 to pi. These are limits for only half the sphere. If you are using only the first octant part of the sphere, then limits will be r varies from 0 to a, theta will vary from 0 to pi by 2, as well as phi will also vary from 0 to pi by 2. Now let us solve some examples on this. In this first example, we are asked to evaluate the triple integral of x into y into z dx dy dz over the first octant of the sphere given by equation x square plus y square plus z square is equal to a square. Guys, this is the equation of a sphere centered at origin with radius a. So let us first draw this volume. So assume this is positive x-axis, positive y-axis and positive z-axis. So if we draw only the first octant of the sphere, it will look like this. Here modulus varies from 0 to radius a. Here given that radius is a. So modulus varies from 0 to a. Theta will vary from 0 to pi by 2. And similarly phi will vary from 0 to pi by 2. Now let us transform this integral from Cartesian coordinates to spherical coordinates using the relation between Cartesian and spherical coordinates, which is x is equal to r sine theta cos phi, y is equal to r sine theta sin phi, and z is equal to r cos theta. We also know that dx dy dz in spherical coordinates is r square sine theta dr d theta d phi. So this triple integral now will look like this. We are getting 1 r from x, 1 r from y, 1 r from z, and r square from dx dy dz. So together when we multiply them, we will have r raised to 5. We have 1 sine theta from x, 1 from y, and 1 from dx dy dz. So together we will have sine cube theta over here because we are taking product x, y, z. And finally, we will left with cos theta, sin phi, cos phi, dr d theta d phi. This cos theta is coming from z, this sin phi is coming from y, and this cos phi is coming from x. I hope you understood this transformation from Cartesian coordinates to spherical coordinates. I have also explained you how these limits came. Okay, now let us start evaluating this integral. First, we evaluate it with respect to r. Integration of r raised to 5 is r raised to 6 upon 6 over the limit 0 to a. Substituting these limits, we will get a raised to 6 upon 6, which is constant that you can take out. Then we have sine cube theta, cos theta, sin phi, cos phi. Now let us evaluate this integrand with respect to d theta. For that, we are going to use substitution. Sin theta is equal to t. After differentiating, we will get cos theta d theta is equal to dt. Let us substitute sin theta is equal to t over here. So we will get t cube here, and cos theta into d theta will become dt. Like this, d cube into dt. So sin phi and cos phi d phi will remain as it is. Integration of t cube with respect to dt is t raised to 4 upon 4. It will be t raised to 4 upon 4 over the limit 0 to pi by 2. Now we will once again write what is t over here. We have substituted t is equal to sine theta because these limits are of theta, not t. So I'll write here sine raised to 4 theta. Now we substitute these limits in theta. Sine pi by 2 is 1, so sine raised to 4 pi by 2 is also 1. Similarly, sine 0 is 0, so sine raised to 4 0 is also 0. So we will left with 1 by 4. It is constant, we can take it out. We have 1 by 24 into a raised to 6 of integral from 0 to pi by 2 sine phi cos phi d phi. To evaluate this integral, I am going to use one of the identity which says sine 2 theta is equal to 2 sine theta cos theta. So sine phi cos phi is sine 2 phi upon 2. Now let us integrate sine 2 phi. Integration of sine 2 phi is minus cos 2 phi upon 2 over the limit 0 to pi by 2. Now let us substitute these limits in phi. When we put pi by 2 in phi, we get cos 2 pi by 2, that is cos pi, but cos pi is minus 1. So we write minus 1 after substituting the upper limit. I'm taking this minus sign out. Then let us substitute lower limit 0 in phi. We will get cos 0, and cos 0 is also 1. So we get minus a raised to 6 upon 48 into minus 1 upon 2. Minus 1 is minus 2. Minus 2 by 2 is minus 1. Minus into minus is plus. So we left with a raised to 6 upon 48. So this is the value of this triple integral evaluated easily using spherical coordinates. I hope you guys understood this example. Now let us proceed for next example. Here we are asked to evaluate the triple integral of 1 upon x square plus y square plus z square raised to 3 by 2 dx dy dz over the volume bounded by the spheres x square plus y square plus z square is equal to a square and x square plus y square plus z square is equal to b square, where a is less than b. Let us see step by step solution. First, we draw this volume over which the integration is to be evaluated. this volume is bounded by two spheres, x square plus y square plus z square is equal to a square, and x square plus y square plus z square is equal to b square. Both these spheres are centered at origin. This sphere has radius a and this sphere has radius b. Since a is less than b, this sphere will be smaller than this sphere. So if we draw these two spheres, it will look like this. And the volume bounded by these two spheres is shown by this orange color. Now let us transform this integral from Cartesian to spherical coordinates using the relation between Cartesian and spherical coordinates, which is x is equal to r sine theta cos phi, y is equal to r sine theta sin phi, and z is equal to r cos theta. We also know that value of dx dy dz in terms of spherical coordinates is r square sine theta dr d theta d. Now let us find limits for r, theta and phi. Note that the volume ranges from this sphere to the other sphere. On this sphere, modulus is A, and on the other sphere, modulus is B. So limits for dr are varies from A to B. So inside integral will have limits A to B like this. Also here theta varies from 0 to pi, and by flipping this at 2 pi angle we will get this hollow sphere. Therefore phi will have limits 0 to 2 pi. Coming to integrand, using this relation you will see x square plus y square plus z square is equal to r square. So this will be r square raised to 3 by 2, and we know dx dy dz is r square sine theta dr d theta d phi. Now we are all set to evaluate this integral. So let's go for evaluation. This will be r square raised to 3 by 2, that is r raised to 3. R square upon r cube is 1 by r, and integration of 1 by r is log r over the limit a to b. When we substitute these limits in r, we will get log b minus log a, which is log b by a, which is constant that we can take out. Now we integrate sine theta d theta. Integration of sine theta is minus cos theta over the limit 0 to pi. When we put pi in theta, we get cos pi, whose value is minus 1. And after substituting lower limit 0 in theta, we will get cos 0, which is 1. So we have this minus sign outside. After substituting the limits, we get minus 1 here. So we have minus 2. Minus 2 into minus 1 is 2. So we left with 2 log b by a outside into integral of d phi over the limit 0 to 2 pi. Integral of d phi is phi over the limit 0 to 2 pi. After substituting these limits in phi, we get 2 pi. 2 pi into 2 is 4 pi into log b by a as it is. This is the value of the given triple integration evaluated with the help of spherical coordinates. I hope guys you understood the importance of spherical coordinates. You can see that these critical examples can be easily evaluated with the help of spherical coordinates. So guys, if you like this video, please click on the like button and share this video among your friends. I will be coming with more such interesting topics in my upcoming videos. Till then, keep watching my videos. Thank you all of you.
Thank you for watching this video. Please subscribe my YouTube channel and press the bell icon to get updates about my new videos.